So let's suppose we know that the sun is a distance of 1.5 times 10 to the 11 meters away from Earth. And we also know that it takes Earth 365 days to make one full orbit around the sun. So knowing that information, we want to calculate what the mass of the sun is. So let's make two assumptions. Assumption number one, the orbit of the Earth around the sun is perfectly circular. And assumption number two, our sun is stationary. So our radius of the orbit, or the distance from the center of masses of our two objects, is 1.5 times 10 to the 11 meters. So let's begin by using the second law of motion. The sum of all the forces acting on the Earth is equal to the mass of the Earth multiplied by its radial or centripetal acceleration created by the sun. So what exactly is the force acting on our Earth? The only force acting on the Earth is the force due to the gravity of the sun. And it's given by the following equation. So we can rewrite the left side in this format. The gravitational constant G multiplied by the mass of Earth multiplied by the mass of sun, which is what we want to find, divided by our radius of the orbit squared. And this is equal to the left side, which can also be represented using velocity and radius, because our centripetal acceleration is equal to velocity of the Earth squared divided by the radius. So this equals this side. But note that we don't know what the velocity is. What we do know is the period of our Earth. In other words, the Earth takes 365 days to make one full orbit. And if we wanted to, we can convert this to seconds per orbit. So we take 365 multiplied by 24 by 60 by 60, and we get the following value. And this is seconds per orbit. So, what exactly is the relationship between velocity and period? Well, it's given by the following equation. The velocity is equal to the circumference of the orbit divided by the period. So we can take this value and substitute into velocity to get rid of our velocity. And that's exactly what we do in step 4. The left side, this is equal to mass times the Earth multiplied by this whole thing squared. So we get 4 pi squared multiplied by r squared divided by t squared times r. So one of the r's cancels, and notice the masses of the Earth appear on both sides. So these guys also cancel, and we're left with the following equation. The gravitational constant G multiplied by the mass of the sun, which is what we're looking for, divided by r squared equals 4 pi squared r divided by t squared. So now we rearrange the equation, we bring everything to the right side, and we leave the mass of the sun on the left side because that's what we're looking for. And that's exactly what we get in step 5. So this is the formula we want to use. So we know every single value on the right side. So let's plug that in. So 4 pi squared multiplied by the radius cubed, 1.5 times 10 to the 11 cubed. And then the bottom becomes t squared. So this number in seconds squared multiplied by the gravitational constant, 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared. And we're left with the following value. So this should be squared on the bottom. So we're left with the following value. 2.0, approximately 2.0 times 10 to the 30 kilograms is the mass of the sun.